I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is curious. We'll start with a nice little visual puzzle that includes a great demonstration of the value of pi. It then disappears down a rabbit hole of mathematical results that illustrate how mathematicians want to completely answer questions. Along the way, we will see something provocatively titled the sausage catastrophe. Here is a standard can of 3 tennis balls. Actually, it contains game-used balls from Wimbledon, but that's another story. We will start with a simple question. Is the can taller or bigger around? Almost everybody sees clearly that it is taller, but you should be suspicious that I wouldn't have asked the question if that was the answer. The answer is actually fairly easy to deduce. Since there are 3 tennis balls in the can is 3 tennis balls tall. By around, we mean the circumference of the circular can. You may remember a formula for the circumference of a circle, 2 pi r, where r is the radius of the circle. The diameter of a circle is twice the radius, so this could be restated as pi times the diameter. But the diameter of the ball is the same as the height of the ball, so the circumference equals pi tennis balls. We know that pi is about 3.14, a little larger than 3. The can is pi tennis balls around. That's greater than the height of 3 tennis balls. It happens that it is easy to demonstrate this result. The can of tennis balls is almost exactly the width of a standard piece of paper. If you wrap the piece of paper around the can, you will find that it does not quite wrap all the way. The can is larger around than it is tall. And this gap gives you a visual for how much pi is larger than 3. That's a fun result, but we can talk about something that is of practical importance. The tennis balls are wrapped in plastic, and the manufacturer would like to minimize production costs by using as little plastic as possible. What shape should the can have to minimize the amount of plastic? In math terms, we want the convex hull of minimum surface area. You might imagine that a flat triangle of balls might be better, but it turns out that the tube is optimal. When mathematicians attack this problem, they characterize the tube as a sausage skin with tennis balls inside. Here is some insight into how mathematics progresses. Having answered the question of the optimal shape for a stack of 3 balls, the researchers immediately wanted the answer for 4 balls, or 5, or any integer. It's unlikely that tennis ball manufacturers will want to package 42 balls at a time, for example, but finding the ideal shape for a 42-ball package might be useful for manufacturers of marbles or shippers of apples. So let's go ahead and completely solve this problem once and for all. The answer is surprising. For 55 balls or fewer, the sausage tube is optimal. For 65 or more balls, a cluster, think of a supermarket stack of oranges, is better. In between 56 and 64, it oscillates, with the sausage being better for 57, 58, 63, and 64. Now, before chaos theory came into prominence, the term for a sudden change in behavior, like the change in optimal shape, was catastrophe. So this result is known as the sausage catastrophe. You might be surprised to find out that this doesn't finish the questions mathematicians ask about this problem. What about the analogous problem of packing 4-dimensional tennis balls, 5-dimensional tennis balls, and so on? It is fair for you to wonder what these questions mean. What does a 4-dimensional ball look like? I don't know, but I can write down an equation for one. You may have seen that in 3 dimensions, x, y, and z, an equation for a sphere of radius r is x squared plus y squared equals r squared. To turn this into an equation for a 4-dimensional sphere, we just need to add another variable, say w, to get an equation x squared plus y squared plus z squared plus w squared equals r squared. Formulas for volume and other quantities can also be extended from 3-dimensional values. So, what happens in higher dimensions? For 4-dimensional spheres, it is believed that something like the sausage catastrophe occurs with a sudden transition from sausage to cluster. The sausage conjecture is that for dimensions of 5 or higher, the sausage is always optimal. Here, conjecture means that the result has not been proven or disproven, but remains an open problem of interest. There is one last oddity to report. The sausage conjecture has been proven for dimensions 42 and higher. I don't know the math of this work well enough to know why there is a proof that works in 42 dimensions but not 41. However, as a fan of Hitchhiker's Guide to the Galaxy, I love the fact that 42 is the magic number. In any case, if you go into the business of packing 42-dimensional tennis balls, stack them up in a sausage.